Hello friends, I hope you all are fine. So this is the part 2 of optical instrumentation. In this we are going to deal with fiber optics, and I am going to discuss the important parameter of the fiber optics like numerical aperture, acceptance angle, and after that I will be discussing about the classification of the optical fiber like step index fiber, graded index fiber, single mode and multi-mode fiber. After that I will be discussing about the characteristic of optical communication and what are the requirements of a good optical communication system. And these points I will be discussing, and at last I will be giving a block diagram of actual optical communication system from transmitting end to the receiving end, like how the optical communication is achieved. So let's start with the first topic, which is optical fiber. And at first thing, let me tell you the definition of the optical fiber. So optical fiber is a cylindrical dielectric waveguide which is non-conducting in nature and transmits the light along its axis. As you can see over here at the axis, core is present. So basically in optical fiber we consider the three parts. First one is core, second is cladding, and third one is plastic jacket. So first point is core. You can see the definition. Core of the optical fiber is the innermost layer in which the light travels. And second point is cladding. Cladding is the portion next to the core and it completely surrounds the core of the fiber. And the refractive index of cladding is lower than that of the core. This point you should remember. Like the refractive index of cladding is less than that of core. Why this is so? As we all know, like when the light travels from denser medium to rarer medium, we observe total internal reflection. And for the optical fiber, the basic principle of operation is only total internal reflection. That's why we use cladding, which is of less refractive index than that of core. The third one is protective jacket. As the name itself is saying, it is protective. So it protects the optical fiber from the moisture and environmental damages. As I said, the principle of optical fiber is total internal reflection. This is the first point you should remember. The next point is the refractive index of the core, which is always greater than that of the refractive index of the cladding. And the third point itself, making a clarity about the concept, like the core is having the highest refractive index, later on it will be cladding, and at last jacket. Jacket is just about the protection. So these two, like you should know what is the refractive index order of the core and the cladding. Here is the first important parameter of any optical fiber, which is the numerical aperture. We call it Na. So basic definition of numerical aperture is it is the light gathering capacity of an optical fiber, like how much optical fiber can gather a light or can take input. In other words, you can say mathematically an numerical aperture is sine of theta a. Theta is the acceptance angle. Here is the definition of the acceptance angle: the maximum angle of incidence of optical fiber for which total internal reflection can take place is called the acceptance angle. You can see more clearly in the diagram itself, like the ray of light which is incident on optical fiber axis, and it is making theta a with the normal. So this angle, the maximum angle, the more is the theta a, more is the light gathering capacity of any optical fiber. So the maximum angle of, value of theta can be 90. So sine 90 is equals to 1. So we can say, like, for a numerical aperture of 1, there will be entire light gathering capacity or ability, you can say. Sometimes in question they ask about acceptance angle. So acceptance cone, which is 2 times the acceptance angle. This diagram is also very helpful in the derivation of the numerical aperture expression. So let's see the numerical aperture expression. So before that, I want to discuss about the refractive index difference. So this is basically the relative refractive index difference, which is delta. So here the n1 minus n2 upon n1. Here n1 is the refractive index of the core, which is written over here, and n2 is the refractive index of the cladding. Okay. Yeah, so let's derive the expression for the numerical aperture. So first you have to apply the Snell's law at point P. So at point P over here, you can apply Snell's law, like n1 sine theta c equals to n2 sine theta r. Here the theta r is 90 degree. That's why sine theta c is equals to n2 by n1, and you can mark it as a 1. Now you can see the triangle OQP. In OQP, here is a 90 degree angle. This is of 90 degree, and you can relate the theta r and theta c. So theta c is 90 minus theta r. And if you put this value in the equation 1, you will get sine 90 minus theta r equals to n2 by n1. So sine 90 minus theta is cos theta. So cos theta r equals to n2 by n1. And you can write cos in terms of sine, 1 root of 1 minus sine square theta r. And here you can calculate the value of sine theta r. Similarly, at the point O, you have to apply the Snell's law. Same. So n air, here the refractive index of the air is an air, and into the sine theta a equals to n1 sine theta r. Here you can see in the diagram and you can apply, no problem at all. So with the help of this, here you have to put the value of sine theta r from this value. So after solving, you can finally come across a sine theta a, which is equals to root of n1 square minus n2 square upon n air. Generally, we take n air as in 1, so the sine theta a, which is equals to the numerical aperture, comes out to be root of n1 square minus n2 square. Okay, this is very simple derivation. You can remember it, or you can directly remember the formula of numerical aperture. So numerical aperture is equals to sine of acceptance angle, which is equals to root of n1 square minus n2 square. Here n1 is the refractive index of the core. Okay, this is very simple formula and you can remember it also. Here 2 points I want to discuss. The first one is I have already discussed, like for a maximum light gathering capacity we have theta a, which is equals to 90 degree. So sine 90 is nothing but 1 only. And the second point is very interesting point, like numerical aperture is inversely proportional to the bandwidth. Like more is the numerical aperture, there will be less bandwidth. If bandwidth is less, then therefore the information transmission capacity of any optical fiber will be less. Okay, so the next important point is acceptance angle. You can call it as AA as well. Here is the definition of the acceptance angle: the maximum angle of incidence of the optical fiber for which the light is incident, it gets totally reflected and hence they travel successfully through the fiber. For this total internal reflection to occur, like the angle for which there is no light which is going to the cladding part and all light is getting reflected from the core cladding interface, so that is the acceptance angle, and it is a maximum angle for which we observe the total internal reflection. As we all know, like this mu is nothing but n air, so n air sine theta is equals to n1 square minus n2 square. This is the equation similar to the, like same as that of what we have seen over here in the case of numerical aperture. Here we consider n air as 1, but if you consider n air not equals to 1, you will get this equation. So the theta a, which is the acceptance angle, is equals to sine inverse numerical aperture divided by mu. Here mu is the refractive index of the medium. Okay, so this is the refractive index of the medium. So these are the two important parameters for the optical fiber. So the next point is the classification of the optical fiber. So based on the refractive index, we have two classifications. First one is step index fiber and next one is graded index fiber. Based on the modes, like how many modes are supported for that particular fiber, there are two types: single mode fiber and multi-mode fiber. First, we consider step index fiber. As you can see, the name itself is saying step, and we all know the unit step or a step signal. Like for the core refractive index, it is 1.5, which is more, and the cladding refractive index is 1.2. So there is a sudden rise of refractive index from core to cladding. Okay, so this is the step index fiber. The advantage of step index fiber is like it is very easy to construct and it's cheaper. So here drawbacks are there. So first you consider is a pulse distortion. Like I can say pulse distortion is nothing but the broadening and overlapping of two pulses like this. If there are two pulses, so this is known as overlapping. And if you are sending this pulse and at the output you are getting it like this, so this is nothing but the broadening of the pulse. In step index fiber, we observe more losses and the information carrying capacity is less. As I said, like the numerical aperture is inversely proportional to the bandwidth. So if more is the Na, less is the bandwidth. For the graded index fiber, the refractive index is non-uniform at the core. Like the refractive index is non-uniform with the core and axis it is maximum. This is somewhat you can observe from the diagram itself, like how the graded index fiber is there. The path of light is sinusoidal or parabolic. Like in this optical fiber, the path of light in step index, we observed that due to total internal reflection, the path was in a straight line and in zigzag manner. But here the path is sinusoidal as well as parabolic. The advantage of step index fiber is like the pulse distortion is reduced, losses are less, and more information carrying capacity present in the graded index fiber. A few disadvantages are it is costly and difficult to manufacture. Okay, now to the second classification of optical fiber, the single mode fiber is there. For the single mode fiber, the core diameter is nearly 2 to 10 micrometer, and for the single mode, only one mode is supported. For the number of modes, like how many paths are present through which a light can travel in any optical fiber, for that V number is defined. This is the parameter by which number of modes or paths present in the light can be determined, in the optical fiber can be determined. So this formula is important, and the formula says 2 pi r by lambda root of n1 square minus n2 square. So the formula itself is very clear, and we have to remember this formula. Here r is the radius and lambda is the wavelength of the light which is used. and the other parameters n1 and n2 are very clear. For the multi-mode fiber, wide core is used and more than one mode can travel through it, and number of modes are v square by 2 for the step index fiber and v square by 4 for the gradient index fiber, and v formula I have already given on the previous slide. This is the v formula. You just put the value and solve it and you will get the number of modes. So the next topic is the characteristic of optical communication. So here we have to consider 3 points, like attenuation must be low, like uh, we want very less power to be uh, dissipated, or there is a loss of power. In that way, attenuation must be less. In case of pulse distortion, we don't want any pulse distortion in our signal or any transmitting information. So this quantity must be low. The next important parameter is the bandwidth, and it should be high just in order to uh, transmit more information. Okay, so this uh, so first let's consider the attenuation. Generally we measure attenuation in decibels per kilometer. So here the formula says 10 by L logarithm of output power divided by input power, and this L is mentioned in kilometers. Generally attenuation is done by means of absorption of light, scattering and radiation. So absorption is like by means of manufacturing material itself. The absorption, like the material itself is absorbing some amount of light. In that case, this loss comes into picture. For the scattering of light, this is also a kind of manufacturing defect. Generally, doping is not perfect, or at the manufacturing end, it is not completely manufactured as per the experimental values. So in that case, scattering is also observed. And radiation is by means of bending of light. Like in case of bending, the light is not reflected back at the core cladding interface, and it is just entering into the cladding and getting radiated. In that way, the radiation loss is there. So the next one is pulse distortion. As I have said, in pulse distortion, generally we have two components, broaden and overlap. If there is a pulse which we are sending like this, and at the receiving end, we are getting it like this. So this phenomena is known as broadening. And overlapping is like, for example, we are sending two pulses like this, and at the output we are getting it like this. So in case of overlapping, there is a loss of information in this particular area. So this is also one of the major drawback, like we don't want it in our communication system, basically in optical communication system. So uh, there must be a time gap between two pulses in order to reduce the pulse distortion. So for the step index fiber, we have to use this formula in order to reduce the pulse distortion. So delta t is equals to n1l upon c into delta. Here I have said like delta is the value over here, and n1 is the refractive index of the core itself, and n2 is the refractive index of the cladding. These two formulas are important, and we can directly calculate the value of delta t, for which a pulse distortion can be uh, avoided. So the next one is the bandwidth. Bandwidth of an optical fiber is maximum number of pulses that can be sent and received without overlap. So that bandwidth depends on the delta t, like how much there is a time duration between all the pulses and how much is the total duration of the pulses. Like in that way we can calculate the bandwidth and how many maximum number of the pulses we are sending. So that is itself is the parameter of the bandwidth. So for the optical fiber, we want more bandwidth in order to uh, have a more information carrying capacity. So these are the preferred characteristic of the optical fiber. Like high bandwidth is required, low pulse distortion, low losses, and low numerical aperture, low core diameter. So here by high bandwidth is just because of more transmission of data. Low pulse distortion is to avoid the losses and maximum utilization of our bandwidth. And if low losses are present, then there will be less attenuation. And this low numerical aperture and low core diameters are basically related to the cost of an optical fiber. So here is one more topic, which is coupling losses. In order to couple two optical fiber, like as we know in optical fiber communication, there are various coupling present, and the losses involved during the coupling is equals to 20 log numerical aperture of sending divided by numerical aperture of receiving end. And here is the two diagrams which I have shown. Like first one is sending and receiving. So here there is a complete coupling of light. As you can see, the diameter of receiving is more than that of sending. So there won't be any loss in case of coupling over here. But in the second case, as you know, like the diameter of receiving end is very less in compared to that of sending end. So there will be a chance that the light will not totally coupled with the receiving end of another optical fiber, and in that case we can say like there are some losses present in the system. So this formula is also important. Like sometimes they ask in the question like coupling losses formula. Based on this you can easily answer. Okay. So the major points of discussion we already covered. So the last is the optical communication uh, system diagram. Like for example, here is our input information. We have to, as a user we are giving information, and by means of encoder or a signal shaping circuit we are just converting it into the required electrical signal. And here is the modulator or a driver which modulates the signal by means of any message signal or any input. And here is the light source, which is generally laser in case of optical source. And we use laser as well as LED, but majorly laser is used. Here is one source to fiber connector, and here is our optical fiber cable. We have studied various parameters like numerical aperture and acceptance angle. At this point they are uh, useful, and with the help of this cable there will be a coupling loss involved in the cable. And here is the fiber to detector connector, and here is the detector, and you can say detector or a demodulator. And here is the amplification of the demodulated signal, and that demodulated signal is finally decoded into the digital signal, and the output is observed at the receiving end. Here is our transmitting end. So this is the general block diagram of the optical communication system. Generally as an optical source we take laser and LED, and for the optical detector we use photodiode and photoresistor as well as a phototransistor sometimes. So these three are the detectors. Yeah, so here I have discussed a few formulas. Those formulas are very important for the exam. And yeah, this is all about the fiber optics, and I hope it is clear to you. And for the question of this particular topic I will be providing in the comment section, and along with the answers. So you can first go through the entire study material, and later on you can try questions which are present in the comment section. And yeah, thank you very much.